Why do brittle materials fail without absorbing energy? Imagine a glass window shattering suddenly without warning. It breaks into sharp pieces instantly, leaving no sign of bending or stretching beforehand. This quick, clean break is a perfect example of how some materials fail without absorbing much energy. Now, let's explore why that happens. Brittle materials fail without absorbing significant energy because they cannot undergo plastic deformation before breaking. Plastic deformation is when a material changes shape permanently under stress, helping it absorb and spread out energy. In brittle materials, this process is almost absent. So, when stress reaches a critical point, they fracture suddenly and catastrophically. At the microscopic level, brittle failure happens through rapid crack growth. Cracks form and spread quickly through the material with very little plastic deformation around the crack tip. The atomic bonds in brittle materials break abruptly without the material yielding or stretching. Because of this, the material cannot redistribute the applied energy, resulting in a clean, flat fracture surface. These fractures often occur perpendicular to the applied load, giving the appearance of a smooth break. Several factors make brittle failure happen so suddenly. First, brittle materials have low ductility, meaning they cannot stretch or bend to relieving stress. They cannot deform plastically to absorb energy, so cracks initiate and grow fast. Second, their microstructure plays a role. The grain structure and atomic bonds do not allow dislocation movement, which is necessary for plastic deformation. Without this, energy absorption mechanisms are limited. Environmental and loading conditions also influence brittle failure. Low temperatures make atomic bonds less mobile, increasing brittleness. High loading rates, like sudden impacts, don't give the material enough time to deform plastically. Stress applied in multiple directions, called triaxial stress, can also promote brittle fracture by concentrating stress in certain areas. Stress concentrations are another key factor. Sharp corners, notches, or flaws act as stress risers where cracks can easily start. These cracks then grow quickly, leading to failure without warning or energy absorption. From a mechanical failure perspective, brittle fracture is a common failure mode where the material breaks suddenly under tensile stress. And like ductile failure, which shows signs of deformation before breaking, brittle failure offers no warning signs, making it dangerous in structural applications. Understanding why brittle materials fail without absorbing energy helps engineers design safer products. They choose materials with higher ductility for critical parts, control microstructure through heat treatment, and design components to avoid sharp corners and stress concentrations. Considering environmental factors like temperature and corrosion is also essential. This knowledge is vital in fields like aerospace and civil engineering, where sudden brittle failure can cause catastrophic breakdowns without any prior deformation signs.